Welcome. Today I wanted to discuss with you the second project for our class, which is the Digital Logic Prototyping Project. And in this project, basically we'll get to learn about some simple combinatorial logic, such as the 2's complement adder, and you will learn how to add 2's complement numbers and how to build a circuit for the 2's complement number adder. But the most important part about the project is that you get to do two types of prototyping. So one is with discrete components on little breadboards that you get to learn how to use. And second one is we'll prototype also with FPGA by writing system Verilog code. So we'll get to program a little FPGA board and write some actual system Verilog code. So this project will have two parts. One about the prototyping with discrete components on the breadboard, and the second one with prototyping on the FPGA. And but before we begin, just some reminder about the lab safety and just the lab rules. Please try to make sure you have the lab in a nice clean state when you leave. Push in your chairs, kind of organize. Try to organize the equipment if you can. And if you have any questions, just let us know. But getting to the exciting part. So for this project, you'll be prototyping a simple 2-bit adder. This is a picture of a breadboard that Kevin made with a 2-bit adder, which has two LEDs that output the sum of the numbers you're adding. There's a carry out bit LED that we'll learn about. In addition, there's a second breadboard that has an extra circuit for converting the binary numbers to little 7-segment displays and actually displaying the number. So when you put in a number with the little switches, the binary number, this converter chip will convert the binary to signals that drive the 7-segment display. So that's actually an optional part for the project. So, but it's kind of an extension. But for the basic one, you just have to work with one breadboard and prototyping all the components on the breadboard. And just to review, we'll learn how to do 2's complement addition and how to build a circuit for adding 2's complement numbers, and then we'll prototype it on the breadboard and also prototype it on the FPGA as well. And one goal of this project is to basically learn how to do these two prototyping styles and kind of differentiate and perhaps get some appreciation for how easy it is today to just write code and upload it to an FPGA versus having to put in all the gates on the breadboard. But still, the breadboard is quite fun, so you can get some hands-on experience with different logic. So the background, for some background, we'll be dealing with 2's complement numbers, and this is a bit of a review from our class. So the idea with 2's complement numbers is that you use n binary bits to represent an integer. You can do either a positive or a negative integer, and we usually assume that the most significant bit is on the left, and then the least significant bit is written on the right. And in that configuration, then the position of the bit in the number specifies the weight or the power of 2 that bit represents. And in addition, the nth most significant bit has a negative sign, so that's what allows you to represent negative numbers, because there's a negative sign and a negative weight. So as a quick example, if you want to represent 13 as a 2's complement number with 5 bits, you can it would be 0, 1, 1, 0, 1. And the reason that's the 2's complement representation of number 13 is that if you expand the bits and then you multiply each bit by its respective weight or the power of 2, the sum will add up to 13. So you have 0 times negative 16 plus 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, and in the end, if you add, so it's 0 plus 8 plus 4 plus 1, which gives you 13. And another example, I can do negative numbers. The negative numbers will always have the most significant bit is going to be 1. So to get a negative number such as negative 14, for example, you do 1 times negative 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. And then if you add it up, you get negative 16 plus 2, which is negative 14. So by basically, again, assigning a weight or a power of 2 to each bit, we can add up the total values and get the integer representation of the 2's complement number. And to perform 2's complement number additions, basically you add individual bit positions, and then you might have possibly a carry out bit that I'll explain. So if just a simple example, you have 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 actually gives you 1, 0. So 1 plus 1, it's going to be 2, but using one binary number, you can only represent 0 or 1. So we need to have another digit, and in this case, the 0 is, as we call, the sum bit. So the sum bit of 1 and 1 is 0, and then the 1 is the carry out bit. So this is the kind of the extra bit that you need to represent the actual sum. And if you're adding numbers that have multiple bits, basically the carry out bit goes to the next bit position. So for example, if we try to add 1 plus 3, so 1 plus 3 is 0, 0, 1 plus 0, 1, 1, 1. So you get 1 plus 1, the sum is 0, and then the carry out is 1. So then in the next, so this is the second bit position, and this is this. So the carry out of the first bit position is the carry in for the second bit position, and then you have, and then you do the addition again. So 1 plus 0 plus 1 is again 0, and then a carry out of 1, and then 1 plus 0, 0 is 1, and a carry out of 0. So at the end, you have the 1 plus 3 is 4, which is 1, 0, 0, so that perfectly adds up. And then these are the 1, 0, 0 are the sum bits, and then the carry out bit is is 0 in this case. So again, you do addition column wise, and then if you have a carry out, you just push it to the next column. Oh, and if you want to convert from positive to negative 2's complement numbers, you also use addition. So for example, to go from 14 to negative 14, you effectively you have to flip the bits of the number. So 0, 1, 1, 1, 0 becomes 1, 0, 0, 0, 1. You add 1, then you perform the regular addition as I just described, and then you get 1, 0, 0, 1, 0, which is negative 14. And I already mentioned that if the most significant bit is 1, then you know right away that it's a negative. That's going to be negative numbers. So converting from positive to negative or negative to positive is the same way, and it's very easy. And if you can convert from positive to negative, then you can do subtraction as well. So if you have an addition circuit, you can do a plus negative b, and that is basically a minus b. So by building a addition circuit and then either converting one of the inputs to its negative value, or maybe even building a circuit to convert the positive number to a negative number, you can do the subtraction. So we'll just build an addition circuit, but as an extra credit, you can do a subtractor as well. All right, so let's get into the details of how to do the addition using logic gates. So to add, so the basic unit for doing the addition is a 1-bit full adder. So as the name implies, the 1-bit full adder adds two 1-bit numbers and generates a sum and a carry out, and then also there's a carry in. So in effect, you have a truth table for the 1-bit full adder that looks like this. You have A, B are the two 1-bit numbers you're adding. Carry in is the carry in possibly from any other addition that you did before using this adder, and then the sum and the carry out. And so based on this truth table, you could come up with the sum of products expression for how to implement the full adder, and you could have a circuit that does a simple addition of two 1-bit numbers. And the reason we have the carry in is that basically you can chain the 1-bit adders together to create n-bit adders. So effectively, you take a 1-bit adder. So let's say the 0th bits get put into first 1-bit adder, then the carry out connects to the carry in of the next 1-bit adder, and then you put in the next position of bits, you add them, and then the carry out goes to carry in of the next 1-bit adder, and so forth until you basically have added all your numbers. And so you can see again, you have at the end you have the sum bits for the addition, and then you have one carry out bit at the very end. So if we go back to look at the addition again, so for each bit position For example, let's do 1, 1, 1 plus 1. The sum bit would be 0, and then the carry out would be 1, and that carry out becomes the carry in for the next bit. So carry in 1 plus 0 plus 1 gives you 0, and another carry out, and so forth. So you can see that by chaining these 1-bit adders, we can do an n-bit adder. And important thing to note that the carry into the very first adder is fixed at 0. So that's important. All right, so we have the circuit. We had the block diagram of the 1-bit adder. We had the truth table, and now we can look at the actual circuit. So here I'm not using the canonical sum of products. Instead, we simplified the circuit a little bit by using XOR gates, some AND gates, and some OR gates, but that still has the same functionality. So this is the schematic, and the schematic shows you the 2 inputs for the 2 1-bit numbers that you're going to be adding. It shows you the carry in that you're going to be also using for the addition, and it has the carry out. In this case, it's Y0. The carry out here, and then the sum, which is in this case labeled Y0, and it has all the logic gates and the connection. So the 2 1-bit inputs go to an XOR gate, and then that is XORed itself with the carry in, and then that gives you the sum bit, for example. And the important thing about the schematic is that it shows you the inputs, it shows you the outputs, and also the logic gates, but it also tells you logic modules that you can use to implement these different gates. So you'll see if you have the breadboard, basically all the logic gates, they're no individual XOR gates, but rather they come packaged in a kind of a dual inline package format, where you have some multiple gates inside one little module, and then you have to connect basically the wires to the modules. And I'll explain this in very shortly. But what the schematic does, it shows you the model number for which module implements which gate. So for example, 74HC86 is the XOR gate. And we'll come back to that in a little bit. But now that you've seen the 1-bit adder, again, we can put multiple of those together to build an n-bit adder. So here's a schematic of a 4-bit adder, and you can see the repeating pattern. There's a 1-bit adder, and then the carry out of the 1-bit adder is connected as the carry in to the next 1-bit adder. So you can see this is effectively 4 1-bit adders, and at the end you have the carry out, which is the last carry out of the whole addition. So so that's the kind of the quick overview of how you can design a 1-bit adder and use that for creating an n-bit adder, and you saw the schematic for addition of 4 1-bit numbers. And now for the first exciting part, we'll talk about how to actually prototype it on a breadboard where you have all the different logic modules, you have some switches and LEDs for the output. So okay, so let's go to this next part. So again, this is the breadboard I showed to you earlier. It's set up for a 2-bit adder, which is the required part for this project. You can extend the 2-bit adder for a 4-bit adder. You can also extend it with the 7-segment displays to show you the different numbers. So they're kind of the basic part is rather simple. So you have lots of time to experiment and try some other additions. To come back, so before we can build the whole breadboard, we have to come back to the schematic, and I'll explain a little bit more about the logic modules that are used. So again, within the schematic, you see the numbers for the logic modules that are used, and basically you can use the logic module number to look up the data sheet, and from the data sheet you would find out, for example, that 74HC86 is a quad 2-input exclusive OR gate. And what that means is that inside the module there is quad, so there's four 2-input exclusive OR gates. So inside each of the little modules for the XOR, there will be 4 individual XOR gates. And if you haven't had a chance to see it, this is the picture of a dual inline package. So it's a little, typically little black-colored package which has legs on either side of it, and it has little dimple on one of the ends. So on the schematic here, you can see the little dimple, and basically you can use that to figure out which is the first pin on the module. So you see there's a dimple, and then there's legs 1, 2, 3, 4, 5, 7, kind of going counterclockwise. So whenever you pick up a little dip module, you can use the dimple and then figure out which is the first leg and the second and so forth, and then you can look at the schematic to figure out which leg connects to what. So you can see that in this example, inputs legs 1 and 2 on this module connect to the inputs of one XOR gate, and then the output is connected to the leg 3. And 4 and 5 connect to the next XOR gate, and the output is connected to 6. So so by using the module number, you can find the actual module, or if you find a module, you can use the number to kind of look up what it is implementing, and you can use the schematic to figure out the actual connections between the gates. And last thing, there are two important legs. So in this case, legs 7 and 14 are the ground and then the VCC respectively. So each logic module you have to connect it to power and ground to actually make it work. And similarly, this is showing the 74LS08 module, which is the AND gate, and it's similar. There's 4 2-input AND gates in one of these modules. And I should point out that the 74 is the series number. The 2 letters typically specify the way the logic gates are implemented. So there might be some high-speed CMOS or maybe a low-power implementation. And then the last 2 numbers specify the functionality. So 86 is the XOR gate, 08 in this case is the AND, and 32 is an OR gate. So so here's the module for the OR gate. So it's a quad 2-input OR gate. So when you have the schematic that has the modules listed, you can really quickly grab the right parts for assembling your circuit. Or if you just have a schematic without the module numbers, you can search online to figure out which module can implement this gate, and that's the one that you should use. So okay, so now let's go back to the picture of the breadboard, and I'll explain about the different parts of the breadboard if you haven't seen it before. So here it is the schematic of the 1-bit adder on top, and on the bottom there's the implementation of the 1-bit adder using the discrete components on the breadboard. And you can see that there's, in this case, 1, 2, 3, 4, 5 modules that I've put on the breadboard. You actually don't need to use all 5 for a 1-bit adder. You can see that all the wires are basically going to just the 3 gates. I've set it up with 5 modules because that's the number you would need for a 4-bit adder. So if you wanted to start, so I suggest actually you start with a 1-bit adder, make sure 1-bit adder works, then connect the other gates for a 2-bit adder, and then you can do 3 and 4 and even more if you wish. So so this is the picture of the 1-bit adder on the breadboard, and I'll go through some of the parts of this breadboard. So first of all, this is if you haven't seen it, this is a breadboard. Couple of important things. One, we have a limited supply of breadboards, so please do not take these from lab. And 2, please put some masking tape and your name on the breadboard to make sure that that if you build some circuit on it and you leave it in lab and you come back later to continue working on it, that you can find your breadboard and that it has all your logic still on it. So that's about some logistics, but what are all these holes and lines on the breadboard? So effectively, if you zoom in, these little vertical columns are all electrically connected. So the way the breadboard is designed is that each of the vertical columns is electrically connected. So if you put a pin or a wire or a leg of a module in one of the holes, then it's electrically connected to all the other holes in that column, but not the adjacent ones. So that helps you with prototyping and connecting. So you connect wires basically by putting one wire in one hole and putting another wire in an adjacent hole in the same column, and this way the 2 wires become connected. In contrast, the red and blue lines, the middle rows, are typically connected from one end to the other end of the breadboard, and these are used for power and ground. So typically the red would be power, and the blue on the bottom would be ground. So you would hook up power and ground, and then if your module needs to have power or ground connected to it, then you would take a wire from this horizontal line and connect it to the module. And you can actually, if I go back, you can actually already see it here. So here, the ground is the black wire. It's connected to the horizontal blue row, and then there are these black wires going from the blue row to the vertical column that connects to the ground leg on the module. So you hook up the power and ground or somewhere on the side, and then you just pull little wires towards your modules as you need. So that's roughly how the breadboard works. And okay, this is again the same picture. And if we zoom in, you see the module a little bit better, and you can see that in this case the green wire is connected to leg 1, orange wire is connected to leg 2, and the yellow wire is connected to leg 3. And then if you look at the schematic, you see that leg 1 and 2 are inputs to an XOR gate, and the output is on leg 3. So we can right away see that the yellow wire is the XOR of the green and then the orange inputs. So that's it's pretty simple. Yeah, I guess you can't see, but the dimple here is on the left. So again, you put in the module in the middle on the breadboard. They're designed. The breadboards are in the dual inline packaged module are designed such that they fit on this part of the breadboard with a little valley. You put it over, and then you can on either side the legs connect to the columns, and then you can connect wires to the different columns. And I already mentioned about the power. So yeah, you connect the power. Usually red is the VDD, and black is the ground, and you connect them to different rows, so you can supply power to all your modules. Let's see. Oh, and in this case, output signals, right? So you have your 1-bit adder with all the connections, and you need some outputs and inputs. So for the outputs, we're using LEDs. So typically, you can put one leg of the LED in one column, and then the other leg on the other side of the valley in the other column, and the anode would be the one here on the bottom in this case. So you supply positive voltage to turn it on, and then the cathode would be connected to the upper column, and then via a resistor to the ground. So you can see that the resistor is plugged into the ground. So the resistor basically limits the current that goes through your LED, and so it doesn't burn up the circuit. And then the LED is connected on one side to ground, and then on the other side it's connected to the output. In this case, this I believe is the sum output of the circuit. So when the sum is 1, so then the circuit generates a voltage level corresponding to logic 1. This LED will turn on, and didn't bring the power supply today, but again, this is kind of the circuit. This is the same circuit you're seeing on the slides. You have the two LEDs. I should mention that it's very, very, very useful to label some of the inputs and outputs, and maybe even some of the gates with masking tape. So here, C out is this LED, Y is this LED, and on the bottom you can see that I labeled the wires. The green wire is A, the orange wire is B, and the black is the carry in. So sometimes we don't have enough different colors of wires to give everything a separate color, so it's useful to label the breadboard. It helps with debugging quite a bit. So I think that covered all of the parts of the breadboard. But there's one important notice that the input here signals are not fully connected. So you see that these wires are kind of hanging, so the circuit would not actually work. You need to plug in the wire into VDD if you want to put in a logic 1, or ground if you want to put in a logic 0, and then it will actually start doing something useful. So you can see again, zooming in, these wires currently are not connected. But otherwise, this implements the schematic that you see on top, plus the output is connected to the LEDs. And here's again the picture you've seen before. So a little bit bigger design that Kevin did with the 2-bit adder, and there's some switches. So in this example, you can actually see the switches. So again, the switches fit nicely over the little valley. You can put legs on the either side of it, and then you on top you connect the outputs to the logic gates, and on the bottom you connect the inputs to ground and VDD. And unfortunately, the masking tape is in the way, but effectively, when you switch the switch, either it makes a connection to ground or makes a connection to VDD. So it's either 1 or 0 depending on the position of the switch. And again, very useful. Some of the switches are labeled A1 and A0, so these are 2 bits of the input number A, and then the other ones are marked with X. That means they're don't care or they're not used. So again, it helps debugging and figuring out which switch does what. So just to summarize, for the first part of the project, you will implement, or first you start to read and understand the schematics for implementing a multiple bit adder, and then you implement the design on the breadboard, or you might need more than one breadboard if you choose to do some extra addition. You might need to debug. I haven't really covered it in the slides, but there will be some debugging, trying to make sure the wires go in the right place, and you have to demonstrate the working functionality to kind of show that you have the 2-bit adder working, and you're welcome to do any number of additions. So at the end, I'll talk about the grading and kind of options for doing some extra things. All right, so for the second part, we switched to something a little bit different. So for the second part of the project, we'll be using FPGAs and writing system Verilog code. So the idea is that, again, we'll be prototyping the multiple bit adder, but instead of prototyping it on a breadboard with discrete logic components, we'll prototype it on an FPGA, and you kind of get to learn what are the differences and what are the kind of advantages. So this is an FPGA board. So an FPGA is a field programmable gate array. It's a little integrated circuit that you can basically reconfigure. So it's manufactured, and then you can program it or reconfigure it to implement whatever logic you have envisioned. There, of course, limits the size of the FPGA chip and the complexity of the gates inside. It limits what you can do with it. But for our class, it's more this small. Even this small FPGA chip is more than sufficient. And the FPGA chip usually comes as a part of a FPGA board. So this is an example of an FPGA board that we're using. And of course, there's an FPGA chip on it, but it has some other additions. So there's USB cable for programming and power. There's LEDs and 7-segment displays for displaying the output, and then there's some input switches and buttons. So instead of having to add in your own LEDs or add in your own switches, it's already built into the board, so it's really nice. You just have to configure the FPGA chip to take the right inputs from the switches or generate the right outputs for the correct LEDs. So instead of wiring things physically with little wires, you'll be writing code that specifies which input or which output goes where, or which logic gates how they are connected. And yeah, so this is a zoom in on. So this is I guess maybe you can't see it so well, but this is the FPGA chip on the board, and as a kind of a very high level 10,000 foot overview. So what's inside the FPGA chip? So inside you have I can think of it as an array of logic elements, or they're also called lookup tables, LUTs, and effectively each of those lookup tables can implement a Boolean expression or a Boolean function of number of variables. So the more fancy the FPGA chip, the more complicated each of the LUTs is, but you can think of that, each one can do typically 4, 6, maybe 8 is the maximum. So there's up to 8 inputs that can be going into each of these LUTs, and it can generate any function of up to 8 inputs, although for our FPGA board is a little bit less. And then all these LUTs are connected by wires, and again, you can configure, in this picture, you could configure the blue boxes to specify how the wires are connected. So output of one LUT might be routed to an input of another, and that's how you kind of connect the logic elements. So To give you a specific example, let's say we want to implement y equals a times b times c plus d, but the logic elements only allow you up to 3 inputs. So this would be a simple FPGA that has 3 inputs for each LUT. So the way you could implement the functionality is you'd do LUT1 could do A and B and C, so 3 inputs going into one LUT, and then LUT2 could implement, so if the first LUT implements Y prime equals A and B and C, LUT2 can implement Y prime or D equals Y. So you'd put in the 3 inputs to the first LUT, configure the LUT to do the end of the 3 inputs, and then the output you would route to another LUT, and you'd configure this LUT to perform an OR between these 2 inputs, and it would generate you a Y, which is the output. It's pretty straightforward. Basically, each LUT implements some Boolean expression, and then you connect all the LUTs together to get the whole design to implement the logic that you want. Now, this is great, but you don't actually want to manually kind of figure out which LUT should be doing what and how you should connect them. So what we'll actually be doing, we'll be writing code. So we'll be writing system Verilog code, which is a hardware description language. And then the tools provided by the FPGA manufacturer basically give it the code, and then it compiles it into the configuration. So you give it a code that will, let's say I want to do y equals a and b and c or d, and then the compiler, the tools will take the code and figure out how to convert it into the configuration for the LUTs. One important note that hardware description language is a description language, so you're not writing a program that runs on a FPGA. Rather, you're writing a text description of how the FPGA should connect the logic inside of it. So again, so if you write like a C or Java program, it's a program that's made up of many instructions, and those instructions get executed on a CPU. Whereas for a hardware description language, you're writing a text description of how the FPGA should behave. So that's important difference. And just to give you a feel really quickly of how it looks. So for example, a system Verilog description of a 1-bit full adder is given here, and on the bottom is the schematic for reference. The names are a little bit different, but you can right away see some very, very, very important similarities. So there's a keyword module, so you write module, and then you write full adder. So let's say that's the name of this module that you're implementing. The module has some inputs and outputs, such as A, B, and C, and are the inputs, and so there's a keyword input, and then you list the inputs. There's a keyword output, and then you list the outputs. And you can see on the schematic that indeed there's A, B, and C and are the inputs, and then C out and Y0 or S are the outputs. So there's the correspondence. And you also see that there's keyword wire, so you have to specify the wires. So on the breadboard, you physically have to plug in the wires to connect different modules. In System Verilog, you have to give a name to each wire. So for example, you can see this, the first XOR gate has some output that connects to another XOR gate, so you have to give a name to that wire that connects these 2 modules. So in this case, so there are 3 wires. Net 1, net 2, and net 3 are the names of the wires. And how are they used? So finally, this full adder module itself uses another module. So it looks like a function call. It's not, but it looks like a function call. So you say, I want to use the XOR module, and then the output of the XOR module, in this case, it's listed first. So the output of the XOR module is net 1, and the input is A and B. So this XOR module, the input A and B would be fed into the XOR module. So you didn't have to define any wires, but the output of the XOR module will go to the net 1 wire. And then this net 1 wire is actually used as an input to the second XOR module. So every wire is either an input, output, or you have to explicitly give it a name, and then you can kind of connect everything. And that's it. So with, let's say, 2, 4, 6, 8, with 10 lines of code, you have defined a 1-bit full adder. And likewise, you can use 1-bit full adders to build a multi-bit adder. So here's an example of a 4-bit adder. Again, there's module, full adder 4, so it's a 4-bit adder. It has some inputs, it has some outputs. Most importantly, here you can see that the input can have multiple bits. So I guess in the first example, it is implied that each input is one bit, whereas in this full adder, each input is in this case, so the input A and B is 4 bits because you're trying to add 4-bit numbers, but the output, like the C out, is still 1 bit because there's only one C out. And internally, again, you define some wire, in this case carry, and you have four modules, 4 instances of the full adder, of the 1-bit full adder, and you can see that the full adder has, so if you go back, the full adder has A, B, and C as inputs and S and C out as the output. So input A of the full adder is connected to the let's say A0 input of the big adder. B is connected to B0 and so forth. And you can see that the carry out of the first full adder is connected to carry out 0, and then the carry in of the second full adder is also connected to carry sub 0. So that's how the carry out of 1 is connected to the carry out of the other. And yes, so it's pretty straightforward. Your textbook has a chapter that talks about the system Verilog. So there'll be some information in the project manual, and you can also read the textbook to learn about writing the code for system Verilog. And actually, all the other projects for the remainder of the semester will be using system Verilog. So you'll progressively learn different syntax and different important aspects of how to write system Verilog. But for the full adder, it's very simple. You just need some inputs, outputs, a couple of wires, and a kind of specification of which modules like XOR and AND to use. So that's pretty simple, much simpler in a way than the breadboard design. So you effectively first you write your system Verilog code, then you synthesize or compile the code into the configuration bits for the FPGA, and then you load the FPGA via the USB cable in our case, and then that's it. And then your FPGA implements the logic that you described. And so if your logic is about adding numbers, then you switch the switches on the breadboard. On the FPGA, and then the output LEDs should change accordingly. So that's pretty much it for the second part of the project. So again, you read the schematic, but now instead of doing it on the breadboard, you translate into system Verilog. And the textbook has some information, and we'll also distribute more information about system Verilog. You might do some debugging, and you have to program and actually show that the FPGA is able to do the addition. All right, so last part, probably most important, is the project evaluation. So again, this project has two parts. So for 90% level, you have to follow the project manual, prototype a 2-bit adder on the breadboard, and likewise implement and synthesize 2-bit adder on the FPGA. So get a 2-bit adder working on a breadboard and FPGA, and then write up the project report. And again, there's for 100%, you can expand the design, and it's very open-ended in terms of what you implement. A quick addition will be a 4-bit adder, or you can do the 7-segment display, or you could do a subtractor. You could do a multiplier if you want. It's kind of unlimited. And then so the basic part is very simple. So you have a lot of time to actually implement other things. And reminder, this project is actually 3 weeks, so you have a lot of time. So I would suggest getting through the required part quickly, and then you can explore all the other possibilities. And you do have the first 2 weeks to complete the breadboard, so we want to make sure that nobody is putting it off until the very end. So you have to demonstrate the breadboard by the end of the second week, and then the third week is reserved for FPGA. And so start early, and you have 3 lab sessions, and there will be some open lab hours as well. And all right, so last but not least, I just wanted to thank Kevin Ryan again for helping with the lab and prototyping the design. Some of the breadboards you can see, like this one was made by him, so it takes some time to to do all the wiring. And Wen and Wenjie for being the TAs and kind of helping with all the labs as well. And here's some references. I took the full adder code from one of the websites, and yeah, that's it. So thank you so much, and enjoy the second project and get to do some cool stuff with the breadboard and the FPGA. So thanks a lot.